Right, we're going to do a help video for space. This is worksheet number 5, circular motion and orbital velocity. The worksheet leads us through using the following equations or formula. The first formula is the centripetal formula for the centripetal force, which is F centripetal is equal to mv squared on r. And the other formula that we'll be using is orbital velocity, the orbit, is equal to the square root of gm on r. So the first two questions here, a car making a right-hand turn is driven in a curve, is testing the use of the centripetal force formula. So, going through this now, when we are asked to find the centripetal acceleration, which is this one here, we can understand that the centripetal force is mv squared on r, but all forces are actually mass times the acceleration. So ma would equal mv squared on r. So the acceleration simply, if you cancel the m's on both sides, gives us the acceleration is v squared on r. And this is quite handy if you're just trying to work out the acceleration. You don't need to find the force and then divide by the mass. So using this formula, the acceleration formula for centripetal acceleration, all we need is the tangential velocity, and that's the velocity that you are travelling in the circle, so at the tangent, and you need the radius. So you don't need the mass of the object which is in turning the circle. So just checking through what the data is saying, we've got a radius of 18 here and we have the tangential velocity of 12. So in a few more moments when you pause the video to attempt this question, we can work out the centripetal acceleration, gives a tick there. And the second part was actually trying to find the magnitude and direction of the force. Now the force, you could go all the way back and use the centripetal force formula if you would like to go again, or you can just simply realise again that force equals mass times acceleration. You've already found the acceleration over here and you just need to multiply by the mass. The direction of a centripetal force is always directed towards the centre. That's its definition. Centripetal force acts, no matter where you are on the circle, it acts inward towards the centre. The second question here, which you can, after pausing the video, you can attempt, is a train going around in a circle. So the train and its carriages have a mass. This time we're given the mass. So there it is. The radius of curvature is 200 and the tangential velocity. This question is asking what is the force applied by the train's wheels on the train tracks. And this is getting at the idea that centripetal force by itself is a apparent force. What causes an object to go in a circle is a force directed towards the centre. But this direction, this centripetal force, this force which pulls things in, comes in a whole lot of different varieties. We could have gravitational forces, we can have electrostatic, and in this case here we have frictional forces. So this is the friction of up here was to do with tyres, and this one here is doing with the train wheel. So take a few moments and apply these formulas to calculate the questions 1 and 2. Question 3 now is asking us to find the magnitude of the centripetal acceleration on the equator. To find the acceleration, we're going to use the formula again, that the acceleration is equal to v squared on r. Now we need to show this time that v is equal to 465 metres per second. So how do I show that before calculating? The second part asks us to calculate the magnitude. We know the direction is towards the centre, but how would I find the velocity on the surface of the Earth on the equator there? Well, we just got to realise that the Earth is just a massive circle, and the circumference, so this is our person over here standing on the equator, and this would be the North Pole here, and we're turning around. This person would move around there once in a day. So using velocity is distance over time. This distance is the circumference, and the circumference is 2 pi r. So that's 2 pi r. And time, we know, is 24 hours. It's 24 hours. We need it in metres per second, so we need to find the radius here in metres, and the time here, 24 hours, into seconds. So firstly, we must calculate the velocity that a person is, and it's given you that it should come out to be 465. Then after that, we will place it into this formula here to calculate the centripetal acceleration on the equator. So pause the video now and have a go at this question. The question we're now about to attempt, which is question number 4 on the worksheet, is a question that was placed on the 2013 HSC. And it gave a diagram of a futuristic space station which is rotating. And it's just simply a circular motion question where this astronaut here, because it's rotating, because there must be a force which is pushing the astronaut in towards the centre as the astronaut goes around. And this force is created by the floor, the surface on which it is, which he is or she is standing. Because of equal and opposite reaction forces, that would give the feeling to the person who is standing there a force going the opposite direction, which the person would experience as apparent weight. So all we need to do is work out a centripetal acceleration here. And we need 1g. So it's testing whether or not that we know that 1g is 9.8. And using the acceleration formula, that the acceleration is equal to v squared on r, we simply have to solve for the rotational speed. And the rotational speed is the velocity here. So we just need to find v in terms of using 9.8 and the radius. Oh, sorry, this is the diameter. So we need to find a radius. Okay, so pause the video now and solve for the centripetal acceleration. The next question, question number 5, is simply testing whether or not we understand that an altitude is an addition to the radius. We are also wanting to find the orbital velocity. So finding the orbital velocity, we're going to use the formula for orbital velocity, which is v orbit is the square root of gm on r. The m and the r, the m is always the mass of the central object. Now the central object of orbit is not the object which is orbiting. In this case, we're orbiting the Earth, so in this case, m is the mass of the Earth. Okay, so we need to find the mass of the Earth. So we've given it up here. The radius is the radius of the orbit. So on the surface of the Earth, it would be the radius of the Earth. So here's our Earth, and if we're standing on the surface of the Earth here, then it would simply be the radius. But we're testing whether or not we understand what altitude is. Now, at altitude, the International Space Station is up here. And we know that this distance here is 370, so we need to find the full radius, which is this length there. So we know that the radius of the Earth, from previous questions, is 6,400 kilometres. So the radius of the ISS would equal 6,400 plus 370. Now don't forget that when we place it into the formula, this must be in metres per second. So that means that we need to find the radius in terms of metres. So these are all kilometres down here, so we must make a conversion. Take a few moments now to answer this question. Right, the Earth has a mean orbital radius about the Sun, and it completes a full orbit in that many days. Now, the mean radial orbit, so that part there, whoops, sorry, that terminology there, we know that going around the Sun, the Earth doesn't form a perfect circle, it's slightly elliptical. So we use the terminology mean orbital radius to even out the actual orbit into a full circle. So that's just another way of saying this is if we were to treat the Earth as a circular orbit. So here we're using the same ideas as the previous question, that we need to work out the orbital velocity. Now, if we need to work out the orbital velocity, we could use the orbital velocity formula, which is V equals the square root of gm on r. To do this, we need to know the mass of the central object. Now, if the Earth is the planet in motion, going around, then remembering that m is the central body of the orbit, the CBO I'm calling it here. So what is the central body of the orbit? It's the mass of the Sun, which is what we are actually asked to do in part V. So we can't use this formula because we do not know the mass of the Sun. We do know the radius of the orbit, but we don't know enough information to use this formula. So we need to find V in another form or another way. So we're going back to a previous type of question where we realise that velocity is just simply distance over time, and the distance is the circumference of the orbit, and the circumference is simply 2 pi r, and we've got enough information to find that. So this here is 2 pi r, and we know the time taken is 365.256 days, but remember we want velocity in metres per second. Well, the distance will be in metres because we've got metres up here, but we have to convert this into seconds. So could you take a few moments after you've done to find the velocity, then after you find the velocity, you place it into this formula here, the velocity of orbit formula, and you can rearrange it to find the mass of the Sun, which is the central body. So take a few moments now to calculate A and B in this question. We move now to question number 7, I should say. And once again, we're looking at a mean orbit. We're talking about the moon this time, and the moon has a mass. A moon has a mass of that many kilograms, and it has a mean orbital radius of that many kilometres. We want the gravitational force. So let's have a think about what we can do here. To find the gravitational force, we know that the centripetal force, Fc, is mv squared on r, and it would actually be the gravitational force that holds the moon in orbit, because it would have to be the centripetal force that is created by the gravitational force. Do we have enough information to use this? But we need the mass of the moon, which we've got. We know the radius we've got, but we don't know the velocity of the moon in its orbit. So we can't use the centripetal force. So we ask ourselves, do I know another formula which calculates gravitational force? And we've got Newton's formula for universal gravitation, which is F equals G, capital M, little m, on r squared. Now I like using the capital M, little m version of this because m is the mass of the centre body of the orbit, and m is the mass of the smaller object which is in orbit. So this would just simply calculate the force of gravity between the centres of the moon and the centres of the Earth. And that would simply calculate the gravitational force. So in a few more moments we can use this. The radius is 385,000, but don't forget that is in kilometres. And we need to know the mass of the Earth, and from a previous question we know the mass of the Earth is 5.98 by 10 to the power of 24 kilograms. So take a few moments to calculate the gravitational force on the moon due to the Earth. Part B asks us to state the centripetal force on the moon that keeps it in a circular orbit. And so we've already worked this out, that the centripetal force, we highlighted to work, must equal the gravitational force, because the only reason the moon moves in a circular orbit is the force of gravity. So the force of gravity here must be the centripetal force. So these two quantities must be equal. So that's the reason why here the clue is the state of the centripetal force. It's simply the same as the gravitational force. Now that we know that this value here that we have just calculated is equal to this value here, we can now calculate the orbital velocity, which is v, using that formula. So the value that we got here a few moments ago, in this point here, that value, which I'll put as a question mark, now equals mv squared on r. And that means that we can, if we know this, remember the little m here is the mass of the object which is in motion, so that would be the mass of the moon. R would be the radial orbit, so it's these two values there and there, and we are solving for v squared. We could use v equals the square root of g capital M on r, where m in this case would be the central body of the moon's orbit, which is the Earth, and r would be the radius of the orbit. But the word hence is being used here, so we are asked to use the previous information to calculate further. So take a few moments now to do it this way, and if you would like to, you can always just check whether or not your answer works or gets the same value if you just simply plug it into the orbital velocity formula. The final slide here just shows you all the answers, so you can check that you have got things right. Oh, you can also check that I've correctly done the things correctly as well. Thank you, I hope this helps.